Welcome to The Explainer. I am so thrilled you're here today because, honestly, we are stepping right up to the mathematical frontier. We're going to explore a truly mind-bending connection between an 18th century historical event and the actual underlying architecture of the generative AI that is literally reshaping our entire world right now. You know, when we talk about modern neural networks, we usually just focus on the massive scale, right? The billions of parameters, the giant data centers required to run them. But beneath all that hardware, it's a foundation of pure logic. It is a fascinating story about how centuries-old calculus is actually breathing life into modern technology, completely transforming how machines understand and generate the world around us.
So, let's start with a really foundational question. How does an AI actually know how to take a blurry sketch, or even just a screen full of completely random noise, and turn it into a stunning, recognizable masterpiece? I mean, you type a prompt into an image generator, and within seconds, boom, it bridges this massive gap between absolute chaos and perfect order. For a long time, the way we talked about this process kind of made it sound like the machine was simply imagining things out of thin air. But it's not magic. It's mathematical translation. It is an exercise in optimization. The AI is essentially solving this massive logistical puzzle, calculating billions of probabilities to figure out exactly how to map a completely meaningless cluster of pixels into a highly structured, photorealistic output.
Okay, let's dive into this, because the answer to how it actually accomplishes this is both beautifully simple and, frankly, mathematically profound. To the AI, creating that image is literally just moving piles of sand across multidimensional space. It's not painting, not in the way a human artist uses a brush and canvas anyway. It's calculating the insanely complex logistics of moving materials from where they currently are to where they need to be. Think of the starting point, that random noise we talked about, as a messy, scattered pile of sand. The final image you ask for? That's a perfectly sculpted sandcastle. Every single grain of sand represents a piece of data, and the AI's entire job is to figure out the exact trajectory required to sweep those scattered grains into their final, intricate architecture without wasting a single ounce of effort. Now, the contrast here is absolutely fascinating, because, get this isn't actually some brand new branch of mathematics cooked up by Silicon Valley engineers. No way. This concept was originally pioneered way back in 1781 by a French mathematician named Gaspard Monge. Back then, mathematicians were trying to solve a very physical, grueling problem during the French Revolution. They needed to figure out how to move massive piles of dirt to build military fortifications with the absolute minimum amount of effort and cost. Like, what is the most efficient way to transport soil from an excavation pit over to a building site? Fast forward to the 21st century, and we get this spectacular Wizard of Oz reveal. That incredibly physical 18th century problem of moving dirt, it has directly become the modern digital application of moving data. And that brings us to optimal transport theory. At its core, this is the math that calculates the cheapest, or let's say the most efficient way to transform one distribution of data into another. And guys, this historical math is the literal secret sauce behind generative AI. Whether you're using Midjourney to create mind-blowing art or ChatGPT to generate text, the AI is constantly dealing with massive distributions of data that need to be transformed. When you're processing billions of parameters, inefficiency is incredibly expensive. You just can't afford it. So optimal transport theory serves as this underlying engine, minimizing the computational cost of generation. It acts as the invisible hand, elegantly guiding the chaos right into structure by finding the path of absolute least resistance.
And this brilliantly illustrates a really key concept. To understand how this works in practice, we have to look at a specific metric derived from this theory, and it's called the Vossern distance. Think of the Vossern distance simply as the mathematical ruler that measures how different two ideas or two distributions of data really are. In traditional statistics, comparing two entirely different shapes of data can be, well, incredibly difficult. It usually results in a really rigid binary answer. But the Vossern distance, it's far more dynamic. It doesn't just tell the AI that two distributions of pixels are different, it quantifies exactly how much work it would take to mold one into the other.
So, in the context of our generative AI models, this distance acts as our ultimate ruler. The AI starts with its messy distribution of random noise, and it already knows what the target distribution, that final image, is supposed to look like thanks to its vast training data. The Vossern distance steps in and measures the precise gap between those two states by calculating the core metric of cost. And in this mathematical framework, cost is simply defined as the mass of the data being moved, multiplied by the distance it has to travel. By measuring the distance those digital grains of sand need to move and multiplying that by the intensity or weight of those pixels, the AI gets a perfect, fully quantifiable roadmap for exactly how to construct your masterpiece.
Let's break down exactly how this micro to macro journey builds step by step during the actual generation process. Step 1, the AI starts with complete absolute noise. Step 2, it uses that Waterstein distance we just talked about to continuously measure the gap between its current noisy state and the target image. And then step 3, it guides the pixels into place. The model iteratively nudges each and every pixel, always taking the cheapest mathematical path calculated by optimal transport theory. And it does this over and over, thousands of times in a matter of seconds, until that random noise slowly resolves, crystallizing into a beautiful, high-resolution image. It is literally centuries-old geometry and calculus, operating at the speed of light.
If these deep dives expanded your mind even a little bit, and maybe changed how you look at the tools we use every single day, then you definitely don't want to miss our next breakdown. We are decoding the universe one explainer at a time, so come join the mathematical frontier. Make sure you subscribe right here on the Robo For Education YouTube channel so you catch our weekly deep dives. You can also follow our Substack for the full source documents, and be sure to check out our site, blog, and the whole shebang. Finally, come hang out and join our Discord to chat with fellow math explorers. We're building a seriously amazing community of curious minds over there, and we would absolutely love to have you in it.
Now, I'll leave you with this one final thought to ponder. We just saw how a mathematical theory, originally designed to move dirt during the French Revolution, became the absolute foundation and engine for modern artificial intelligence. I mean, it really makes you wonder, right? What other centuries-old mathematical theories are just sitting quietly in textbooks right now, waiting to solve our most complex future problems? What other metaphorical piles of sand are out there across science, medicine, engineering, just waiting to be moved? Think about that for a bit. Thanks so much for joining us, and I will see you in the next explainer.